Thank you. All right. Let's get started with the last lecture. So, in the previous lecture, we talked about the idea of probabilistic cataloging. I promise this one will be not so statistics heavy. Instead, I will just use probabilistic cataloging at the very end of the lecture, just to highlight some results. However, most of it will be actually about first strong lensing, and then in the second half of it, we will talk about lambda CDM at small scales and how we use strong lensing to probe lambda CDM at small scales. However, first the discussion will be directly on strong lensing. I'll just highlight some features of strong lensing, why it's useful, and then we'll discuss lambda CDM at small scales, and finally talk about probabilistic cataloging's application to this problem. So first, strong lensing. So if you just, going back to just the Newtonian theory of gravitation, if you just take Newton's theory at face value, in addition to the gravitational theory, also talk about, also think about the corpuscular theory of light. So those two together at the same time. Then you actually arrive at the conclusion that because acceleration is mass independent, these light particles, or what they used to call as corpuscles, had to be actually deflected by the existence of mass. So Newton's gravity coupled with the corpuscular theory of light already predicts that light particles must be deflected under the effect of gravitation. And this can be characterized simply by this formula, F is equal to ma, and or rather the definition of the acceleration, and that basically gives you some ellipticity, and through that you can figure out what deflection you get. That's about 0.8 arc seconds for the deflection of stars around the sun. That was a value predicted by the corpuscular theory of light. However, it is unfortunately wrong. And it was realized that it was wrong when gravitational theory of Einstein came in, that is the general theory of relativity. General theory of relativity also predicts that light particles must deflect under the influence of gravity. However, in GR lingo, we usually don't think about light particles, but rather we say light follows the straight path, but that straight path globally is curved. So as a result, for the observer, there is a deflection of light. And that is given by 2 times the Schwarzschild's radius over r, and that basically gives us the right deflection. And using that, we can do a lot of very useful science, which I will come to. And this essentially defines so-called gravitational lensing, which is the lensing of light due to gravity. And in gravitational lensing, one important aspect is that there is no focal points, because I'm sure you will start making analogies with respect to optical lensing that you might be familiar with, like when you have actual lenses. When you have a lens, for example, you usually have a focal point. So if you have light arriving from infinity, they can be focused onto a point. However, in a gravitational lens, because the amount of bending of light or refraction index actually depends on where you are in the lens, you actually never focus all the incoming light rays into a point, but rather into a line or onto a line. So that is the difference between the two. So this is just an artistic picture of what's going on. So you have some galaxy, some light source, and then there's some mass distribution in between the galaxy and you, and then the light rays that originate from that galaxy are bent towards your eye. So that's gravitational lensing. And through this, obviously, you can start probing that mass distribution in between. Strong lenses in the real universe look like this. These are galactic lenses. So you basically have almost like in some of them you can actually see the arcs very clearly. So there is a there's a host galaxy in the foreground that itself is luminous, and at the same time it contains some mass. That mass deflects light from background, and eventually you get these arcs and arclets due to the strongly lensed background galaxy. I will actually come to the definition of strong lensing real soon. So there's the geometry involved. So this is just a schematic showing the geometry involved with this problem. So you have the so-called lens plane and the source plane and you, the observer here. So a couple of important angles here. There's the beta angle, which is the angle on the source plane, and the theta angle, which is the angle on the lens plane. And then there is the difference between the two, which we will call alpha, and that alpha will be the deflection. However, that alpha is not this alpha. This alpha is alpha cap. That is a different alpha. They're proportional. So the proportionality constant is given here. So DLS is the distance between the lens and the source, and DS is the distance to the source. And just basically, just one important point about these is both beta and theta, they're small angles. So we make the small angle approximation. So that allows us to just write basically this whole thing as the sum of this guy and that guy. And that is essentially mathematically written here. So theta ds is equal to beta ds plus alpha hat times DLS. Just going back here, alpha cap times DLS is this guy. That plus beta times ds gives you theta times ds. That's just in the small angle approximation. And using this, we arrive basically at equations that describe what alpha is. And oh, I skipped this one, I should also mention. This is the lens equation, famous lens equation that allows you to map basically after the prescription of some alpha, you can start solving the mapping between theta and beta. And that gives you how the lensing is going to happen. Okay, so this is a special case of lensing where you have just two bodies. So you are walking essentially a background source along this line, and those two lines of images are what you actually see. So when you have two bodies, one lensing the other, the impact factor replaces your theta, so you get this deflection alpha. And if you just substitute in your lens equation, you basically get two solutions to it. That means that you will get two images, so this guy and that guy. And there's also a definition here, which is theta sub e. It's the Einstein angle. I will just come to that. But here there's a nice GIF, so I just wanted to show this. So that background source is moving, and eventually, so you see the white images, which is really fun. So for the deflection, I defined what deflection is. It basically is the mapping between theta and beta. However, in general, just you can write it as a sum over the point masses in your lens plane, and that gives you this definition. For example, for the 2.2 lenses, whenever you have 2 points in the lens plane, that becomes your deflection field. That's not a very typical situation, however, because typically you have a continuous distribution of mass on the lens plane, and we will come to that. So for that, you actually start taking integrals. One thing I should define is so-called the lens potential. So if you just think about your Newtonian gravitational potential and integrate over the line of sight and multiply by some constants, then you get a potential. And once you get a potential, you can start working with that potential to take derivatives, first to obtain your deflection field, and then obtain so-called convergence and shear, which I will come to. So this one is known as the distortion matrix A. It is basically the partial y, partial x, where y is the position on on one plane and x is the other, and you get a drag delta that becomes the second derivative of your potential. This potential is just useful as a construct, but it's not physical, obviously. There's also second-order lensing, because I just provided the first derivative, so this guy. However, there's also this guy. However, we usually neglect it because for most applications in astrophysics, they don't matter. However, there are certain applications in which you have to include it, which I will not talk about. So coming back to this distortion matrix A I defined, you can decompose it into two components. There's this 1 minus kappa, and there's the gamma, which, by the way, is anti-symmetric, as you can see. This very first term is called the convergence, and the second term, this anti-symmetric trace-free term, is called the shear. They act very differently on your images, and very independently, in fact. The definition of kappa in terms of your physical quantities, it's just the surface density of mass divided by the so-called critical density given here, again, in terms of your effective lensing distance, and the surface density of rho, which is the mass density. So you just integrate it along the line of sight using the thin lens approximation. Thin lens approximation is useful simply because for most of the applications in astrophysics, the lens itself is much smaller compared to the line of sight distances. So you can actually just assume that all the mass lies inside a plane. That makes the calculations very, very simple. So this shear term I was just talking about is, as you can see, has cosines and sines. And as a result, its effect on a particular source feature is like this. The convergence either makes it smaller or larger, and the shear essentially stretches it along an axis and squeezes it along the perpendicular axis. After the so this is just an effective description, because you've just defined the potential and you're taking derivatives, forgetting about this higher order term. So there's really nothing about the Newtonian or gravitational. That prescription only comes when you fix alpha itself, and that alpha, yes, it does come from gravitation, GR, basically general relativity, if you want to get the amplitude right. But they are only different up to a factor of 2.
But in general relativity, there exists a general definition of shear as a property of geodesics of space-time.
I see. Okay, but that's the shear of the space-time itself, right?
Space-time.
Yeah. So
geodesics.
I see. Yeah. Okay. I think they're related. Yeah, I think they're related. Yeah, yeah. I mean, this is like essentially a transformation between two planes. So I think they're related in that sense. Okay, so going back to where I was, this guy. All right, so there's just one more definition. I have been talking about this distortion matrix. If you just take the derivative and inverse it, you get the so-called magnification in terms of kappa and gamma. Magnification is a really important object because it tells you how much or by what factor given feature on the lens plane is magnified when you see the same feature on the image plane. That's the mathematical definition. And when magnification is infinite, we get certain contours called critical lines on the image plane and caustics on the source plane. Those are very important lines. So on the source plane, let's just look at this row first. You get here, for example, the source is aligned almost with the line of sight. So you get two surfaces. So basically, inside this geometric shape, you get 5 images. Outside it, you get 3 images, and outside that, you get 1 image. So at the very outside, you essentially just get ordinary lensing, whereas inside, whenever magnification goes infinite, your number of images has to increase by 2, and those 2 images are either created or destroyed at the critical lines. And So that basically means that you can only have an odd number of images, either 1, 3, or 5, with the condition that your mass distribution is always finite. So this is not true when you have a point source, because if you remember in the previous slides, I just showed the two-body case in which there were only 2 images, so that doesn't hold up here. But another thing to show is the cusp and fold caustic. So if you put your background image at the cusp, you basically, on the image plane, what you observe looks like this. By the way, this is known as the Einstein cross. I will show a real example of it as well. In the cusp, you get this large image. However, I will just mention that this, and that, those 3 are separate images. They're not the same. So there's 1, 2, 3, 4, and 5 at the very center. There are 5 images. Similarly for the fold caustic, now you're very close to the fold here, and then you again have 5 images, but in a very different fashion. So similar stuff here actually. Maybe I shouldn't even repeat because I don't have much time. I'll just show here one more relevant thing, which is that if you project the same thing onto the luminosity space, so as a function, so on the y-axis here you have magnification, on the x-axis you have time in units of Einstein time, which is the crossing time of the Einstein radius, and or Einstein angle in this case rather. For different lines, for example, for the yellow line, you don't get infinite magnification, so you follow that line in terms of magnification. For the gray line, you actually do cross that, so you basically get this. And for example, for the blue line, you actually cross it multiple times, so your magnification is infinite multiple times. So by counting them, you already know what type of caustic you've crossed. Now, I've talked about strong lensing only, but there's also weak lensing. If the weak lensing is the situation where your kappa and gamma are much less than unity. So in that case, you have no multiple images, but rather just a slight stretching of your nicely Gaussian background sources. So for example, if you start with sources that look like this, they're not, they don't have to be circles, but they are essentially weak lensed into a weird shape, essentially due to the non-zero, but still very small gamma. Essentially, there is only stretching, but not much convergence here. I really won't go into much about detail on weak lensing because that's really out of scope of this talk. Similarly for microlensing, but I just wanted to mention it. Microlensing, this is the situation where you don't resolve light. So when you have, for example, all the flux just fall in the same pixel, you actually cannot resolve the multiple images, but you still do get the magnification run as a function of time. So you get pictures like this, where as a function of your impact parameter, the magnification looks, or at least its amplitude and also shape, looks different. So you can then use this to count, for example, massive compact objects in the galaxy, which I've already talked about. So typical data that we use for these types of applications come from the HSD. The reason is simply because it's got really high angular resolution. For especially galaxy type lenses, you need a resolution of order 0.1 arcsecond, and that's only available in space. If you're on Earth, then atmosphere doesn't allow you to resolve images down to 0.1 arcsecond. Usually you're seeing limited, which means that it's like an arcsecond. Skipping that, the real universe, in the universe, the real strong lenses look like this. Basically, this is a really happy one. It's almost like smiling. But what actually is happening here is there are two foreground galaxies. They're elliptical. The reason they're yellow is because they're highly evolved elliptical galaxies. That means they're at the very foreground, very evolved giant ellipticals. And then you have these blue arcs and arclets. They come from background galaxies, which are young. As a result, because they're young, they produce a lot of UV radiation, and then they're blue, despite the fact that they're slightly redshifted. So you can tell that whenever you look at these arcs and arclets that are strongly lensed, they're usually much bluer than the foreground colors. Now, there's a special object called an Einstein ring, or rather Einstein-Colson ring, and that's whenever there's a syzygy, that is, there's like basically a alignment of the foreground and the background object. If there is a perfect alignment, then it's a perfect circle, and the radius of that circle would then be the Einstein radius. And typically, we have Einstein, for example, for a cluster scale objects, the Einstein radius is about 1.5 arc minutes, which is really large, by the way. It's like 90 arc seconds. So you really resolve these and a lot of other things in between. For galactic type for galactic type halos, these are like 0.9 arc seconds. Really, it's very close to the resolution limit of space-based telescopes, almost. So basically, you have to have space-based data to actually find these and characterize them. So if you really don't like these guys, the Einstein rings, I have a different picture which is from Interstellar. So same thing is happening here. There's this guy at the background. The only difference is in the background now you have an extended image, extended object. So it's not like a pure ring, but rather a ring-like object, and then there is the disk in the front. So that's how we produce the image of a black hole. Okay, so this is the Einstein cross as promised, just showing the real Einstein cross, how it looks in the universe. And there's also strong lensing in the cluster regime, clusters of galaxies. So here, for example, it's not obvious, I think, but there are like arcs in these clusters where the foreground giant ellipticals basically have so much mass that the foreground galaxies can essentially are strongly lensed and produce arcs and arclets. Just very quickly, this lensing is very useful when you're trying to probe cosmology. One thing you can do is you can probe Hubble's constant with lenses. And the idea is if you already have a handle on the mass of the lens, then you can ask the following question. Given this image and given my prior information about what the mass of the structure is, can I actually constrain the Hubble constant? Because the Hubble constant is in the angular diameter distance, and the angular diameter distance sets this d sub ls and ds and d sub l that I was just showing. So they are sensitive to the Hubble's constant. So you can actually constrain Hubble's constant via these guys. And I don't know if you're familiar with, but currently there is actually a tension between late and early universe measurements of Hubble's constant. And this certainly adds to this discussion, but I don't have time to really talking about that. The very last thing I will mention in this part of the talk is lensing as a probe of substructure, which will essentially set the stage for the remainder of this lecture. I've already talked about this in the very first lecture, that there are many subhalos predicted to exist by lambda CDM. That's just because in lambda CDM, dark matter is cold, so we kind of predict the existence of these, and you can actually use lensing to probe the existence of such substructure. Talking too fast here. Okay, so lambda CDM at small scales. So this is just the plot version of what I was just showing pictorially. So in this plot, you have the maximum velocity on the x-axis of a given halo, and on the y-axis, you have the cumulative distribution. Now, these guys, about 10 kilometers per second, are the ones that are already observed. We have a couple of known dwarf orbiters of our own galaxy. These are known as satellites. And lambda CDM simulations can probe basically the distribution down by almost an order of magnitude further. However, as you can see, there is no observation past about 10 kilometers per second downward, which means that we really have no idea what's going on here, except theoretically. So theoretically, yes, we do have a model called lambda CDM that predicts that there must exist many thousands and billions of these guys at small scales, but we really have no observational clue that they actually exist. And the idea is to use lensing to actually find them, or at least the tip of the iceberg. Obviously, you have no hope of finding things that are, let's say, like Earth-sized or even like Sun-sized, but at least if you can find substructure that is like 1 million solar masses, then you might actually be able to constrain or at least test lambda CDM at a really important limit. Okay, so these are the known satellites of our own galaxy. You may know some of these names. As you can see, the luminosity does vary a lot. However, the mass is about 10 to 7 solar masses, and we really don't find enough of these guys. This is known as the missing satellites problem, because despite the fact that by now, after the dark energy survey, we even doubled the number of known satellites, we still are not finding them at the rate that we should be in order to match up with the predictions of lambda CDM. So there's still a missing satellites problem. So, by the way, you may be wondering why, for example, these small halos are actually dark if they exist. The reason is, in the reionization or during reionization, because the gas gets reionized, or that is like it basically the protons get separated from the electrons, you really cannot cool the gas to produce stars in such small halos. So in that sense, the star formation is said to be so-called quenched in those very small mass halos. So even though they exist, they should not be containing stars. So we don't actually expect them to contain stars. So that is a theoretical expectation that comes from stellar formation models. Okay, now coming to actually constraining dark matter substructure, there have been many works on this, probably first by Dalal and Kochenek 2002. So people have been trying to constrain at least the mass fraction of substructure in such systems, and the ballpark number that people quote are about 1% for typical galactic halos, and this was one of the first results. This is more recent, 2012 from Baghetti et al. And the idea is they study like galactic, galaxy type strong lenses, and then by modeling it, they can actually try to infer the existence of substructure in addition to the smooth halo in the foreground. So, by the way, don't get me wrong, there is a smooth halo in the foreground, the mass distribution. What we are interested in is substructure that sits on top of that. So there is additional structure than the smooth halo. Now, coming to the very end section of this lecture, probabilistic cataloging of dark matter halos. So now you need to just remember some material from lecture 3, previous lecture. So just one note, these subhalos or substructure that I have talked about, essentially, when you think about their mass profile, they're essentially broken power law, but they have a tidal cutoff radius as well. The reason is, I've talked about this in the first lecture, but there's the structure formation is a continuous process. So at any given time, there is always some dynamical friction which starts to rip away material from small halos, which get accreted by the larger and larger halos in which they live. So essentially, for any given substructure or subhalo, there will always be some truncation radius, because they cannot extend infinitely far away. So we model these as well, and the typical images that we forward model look like this. Unfortunately, it's a little too bright for you to maybe able to see all the details, but what's happening here is there's a foreground galaxy. The basically darkness here means more photons, so this image is very bright at the very center. That's the host galaxy, and almost juxtaposed with the same host galaxy is the source. However, it's actually slightly misaligned, so you get these strongly lensed arcs around the host galaxy, and the idea is to be able to model these so as to be able to infer the existence of these substructures shown with the green squares. That's the idea, and we do probabilistic cataloging in order to solve this problem. It is slightly different from what I talked about in lecture 3, because I only gave examples from photometry problem where you're given an array of pixels, that is an image, and you're trying to infer the positions of point sources. Now here, you're still given an image, however, this time you're sampling from the posterior probability distribution of a different catalog space, which is the catalog space of these subhalos as opposed to the catalog space of point sources. It's slightly different, but certainly related. And I will just skip the probabilistic graphical model associated with this because the idea is very similar. It's just that the parameters are different. Instead of now fluxes, you now have so-called deflection strengths, which are proportional to the masses of the subhalos. So it's actually not that complicated, but I will skip it not to confuse you any further. So at the end of the day, what you're interested in is you're given an image, the strongly lensed image, you're trying to infer the distribution of mass on the lens plane. That's the takeaway message, and that's this guy. So the ink here is mass per pixel, so mass density, surface mass density rather. And basically this is in units of convergence. And what you're doing is you're doing these bursts, deaths, splits, merges, all the transdimensional moves that I talked about, all the within model proposals that I talked about, all the internal things about PCAT. Once you run PCAT on it, this is the posterior you get after marginalizing over the number of subhalos. Now, this is really important because if you just look at it's a little too bright for you to see the correlation maybe, but there's a really massive green cross here. There's yet another one here, and those two are very well constrained by the ink. So the ink actually corresponds to where the green crosses are.
The result is the green, which...
No, sorry. I'm using the same notation as lecture 3. Let me just reiterate that. Green is the underlying truth. It's the simulated one. Sorry. So green is simulated. Ink or like color scale is the posterior. Okay, so they agree. And this is just to show basically the distribution of deflections across the image. So you can see that at most they go about an arcsecond, which agrees because that's about an arcsecond. So that basically corresponds to the strongly lensed arcs and arclets. There's a bimodal distribution. So the takeaway message from, I will just skip this one because I'm really running out of time. The takeaway message from this is that you can actually start constraining the mass distribution on the lens plane regarding the substructure, and that is a really, really important tool for constraining deviations from lambda CDM, because different extensions to lambda CDM predict different abundances for such subhalos. So if you can actually do this carefully after the introduction of better data, because I haven't really talked, but current data sets are not really good enough for us to constrain subhalos that are as light as, let's say, 10 to 7 solar masses or so. Current limits, obviously this is a really ballpark number because this changes from lens to lens, but the best typical values we get are like 10 to 8 solar masses, so 100 million solar masses. This is really not enough to constrain deviations from lambda CDM, given all that cosmic variance you have. So you really need better data, much better uncertainties to really constrain this. But this is really futuristic because with coming data sets like W1st or even JWST, whenever it starts measuring strong lenses, we will be able to really get much better uncertainties on these. Just one more point about subhalos. Now, I've mentioned that it's great that we can actually model subhalos. However, if you just look at the problem from the other dimension, some modelers or some people are actually interested in the hosts themselves, not in the substructure. Sometimes substructure is a nuisance for you. So sometimes you just want to be able to marginalize over it. And if you do so, you get these plots. So here, for example, on the x-axis, you have the ellipticity of the host galaxy. And on the y-axis, that's just the number of samples per bin. So it's the probability density function. So after marginalizing all those subhalos, the substructure, then you get a posterior on the ellipticity which has been marginalized over all the nuisances in the problem. So this is kind of cool and very different from the traditional way of looking at this problem. So with that, I'll just show you one more plot, which is kind of our money plot. So this is the fraction of the substructure inside the Einstein radius, which is typically the value people compare across different papers. So green, again using the same notation, is the true value because this is simulation. And then blue is the posterior, and you can see that they agree to 1 sigma. So that means just taking into account the subhalos, we are able to predict nicely the amount of substructure to about 2% in the image, the total image. And I will again skip this. These are a little too detailed, so I'll just skip those. All right, conclusion. So strong lensing, I think, is a really, really important probe is a really important probe to study the universe, the mass distribution in the cosmos, and the application of probabilistic cataloging essentially exploits the idea that we can do probabilistic cataloging to conserve even more information, and we can then basically drill down to about 200 million solar masses at the moment, and certainly with better data sets, we can do better. With that, I'll stop and get questions, and thanks for listening for all the lectures. Okay, so I do have some time now for questions. Yes?
What is the main limitation of current data sets for this method?
Sorry, main what?
Limitation of the current data sets.
That's a really good question, actually. It's rather the exposure, actually. So HST has a really small effective area, Hubble Space Telescope. So Hubble Space Telescope has the angular resolution. It can go down to about 0.1 arc second. The problem with it, so it can do galaxy-galaxy lenses, or at least most of it. The problem with it is you have to ask for 10 orbits, at least, to actually get a decent image of a strong lens that can really compete with substructure analyses. So that is the hard part. That is, I mean, time is money in astrophysics. So you have to ask actually for that amount of time, but many other groups can do a lot of other science with it. So it's like trying to beat down the noise with a really small aperture. If you actually can do this with a much larger effective area, then you can actually collect a lot more photons. And obviously do this for many more systems. So there are two types of uncertainties here. There is per system uncertainty, which is what I just described. There's also the cosmic variance. Like you could get the best uncertainty on Earth for a particular system, but the values you'll get from the other system will be wildly different and will also have a small uncertainty. That should tell you something. What that tells you is that it has cosmic variance. Even though per system you can constrain, let's say, the amount of substructure, that amount of substructure first will change as a function of redshift. Second, it will change as a function of the type of the galaxy. Third, it will just change due to cosmic variance and like due to the secondary interaction terms, etc. So, which means that you need to first have 1,000 such realizations to do a population model, just to sample from that cosmic variance. Yes?
I have one naive question, maybe I missed something. So how you are observing the change of the magnification? Because finally you are getting one image after getting lensed. So when the light ray is crossing, how you can understand? How you can basically be in a different time zone? Because you are getting the final image at the end.
Yes.
So how you can understand that, how it is crossing the lens field?
Okay, I see. So this source lens observer schematic I showed is just a very crude model. And what you're referring to is certainly a good point, because in cosmology, imagine you're looking at a galaxy at redshift 2. There are billions of galaxies in between structures. Like really, I mean, I'm talking about very, very small things, like very small clumps. At least there's the Lyman alpha forest, for example. So that means you have to kind of make an assumption that there is a lens plane, and that only holds true for a subset of such systems. Some systems, you just do the best you can do, and you still get really bad chi-squares. That just means that your single lens plane approximation is no longer true. Then what you can do is you can maybe break it into two, and then try that. Leave the redshifts free, etc. And then maybe...
Which value of Hubble constant this strong lensing measurement suggests? And as you have time, can you just comment about the H0 tension?
Yeah, so the H0 tension, right, so basically the Planck, yes. Okay, so this is the value they get from Planck, basically, 67.4. This Planck is the CMB experiment. That's a very early universe experiment. And this is from the DES BAO. That's also early, well, early-ish, well, relatively later, but still early universe. But then you get from the local universe, the purple data point. And SHOES, I think, is just another lensing experiment. And holy cow, the weirdest name. It stands for H0 something something. They just made it holy cow. But so that gives you yet another data point. So what I'm trying to say is there's some disagreement between the two. And if you ask the theorists, they can come up with 1,000 models that explain these two. But basically, these lens measurements just started, I think, more recently sitting in between the two. So we may really be looking at a redshift evolution of something at the moment. So as you can see, there are many lenses that contribute to the same data point. So there's like every lens gives you an independent and slightly different posterior. So if you were to take these really seriously, you could actually make a map of your posteriors as a function of mass, as a function of redshift, and then you get like a cosmic tomography. The problem is these individual posteriors are really not too tight. So this essentially comes back to my point about per system uncertainty. More questions? Yes, please.
So you said that you were measuring substructure in order to search for deviations from lambda-c.
Yes.
But the substructures you're looking at are subgalactic scale?
Yes, yeah, more like dwarf galaxies and smaller.
Right. So that substructure is also affected by the actual matter component, not only the dark matter. Gas flows, supernova explosions, star formation.
You're right, yes.
So are these, now that doesn't have anything to do with data gathering. You can have a very good explanation of substructure, but what do you need to do to map that onto a measurement and a verification or not of lens?
Yeah, that's a good question. So that baryonic feedback that you mentioned certainly is a factor. However, that is still subdominant because what we probe with this is mostly dark matter, and that dark matter component doesn't talk to the baryonic matter except the fact that they do gravitationally are coupled, and the baryonic matter itself is affected by the processes that you mentioned due to the gas outflows and stuff like that. So there's...
The matter is not dissipated, right?
It is not, yeah.
The interaction with baryons provides the dissipation.
Yes. So in fact, I mean, I did not count this, but maybe I should just enumerate these things. But there are multiple ways to solve the discrepancy of lambda CDM at small scales, one of which actually is baryonic feedback. However, baryonic feedback is kind of like your null model. It's the simplest model, simply because you don't have to postulate the existence of a different of a different particle. However, like when I say different particle, I mean a mediator, either in the self-interacting dark matter model. At the end of the day, you don't want to increase the complexity of your model. So baryonic feedback seems to be the most simple model to explain this type of disagreement. But I think there is, when I say this, some people might not like it, but my impression is that there is a consensus that baryonic feedback itself cannot account for this. It's certainly, just like the massive compact objects, it can account for some fraction of it, but I don't think it can account for all the smoothness at the small scales, at least in the way, in the structure, in the amount that we see. But it can certainly add to that. And I think your question then naturally leads into how are you going to disentangle them? That is the million-dollar question. I don't think anyone has a clear answer to that. I think the only hope is to do a really detailed hydrodynamical n-body simulation with baryonic feedback, take that out, like pretty much model it, and take that out of our measurements, and then see what's residual, and then start interpreting that in terms of dark matter, warm dark matter, self-interacting dark matter, fuzzy dark matter, etc. Yes.
So, do you think that these strong lensing measurements can give some constraint on the sum of the neutrino masses? Because I expect that if I increase the mu, it means my power spectra at small scale will damp, so I'll have less structures than I expect, and so it will influence the lensing.
Yeah, I'm not really knowledgeable on that. It might have an effect on weak lensing. I wouldn't say it might show up in the substructure due to in the strong lenses, because in this case we are in the very, very nonlinear regime. So I think it more affects the linear regimes, or like the Lyman alpha forest regimes.
I think the bound on neutrino masses really comes from the linear regime, where you need a very precise theory of structure formation that doesn't exist in this case.
Yeah.
And you can get that information
From elsewhere, yeah, exactly. Yeah, you have other better probes for that. Any other questions? We have 1 minute. Okay, if not, let's call it a day. And I will be around for other questions as well.